morning. In the last few classes we have been talking of chemical propellants. We have been trying to find out what are the characteristics which we must look for in chemical propellants. While doing this, what is it we have done so far? Let's take a stock of what we have done so far. Suppose I have propellant like, let's say, HNO3. We said it's an oxidizer because it consists more of oxygen than a fuel, and then I react it with something like a hydrazine, which we say is a fuel. Maybe we get products, and these products could be H2O, could be something like N2, could be something like this. This is a completed product of combustion, but if the temperature we said is high, this could dissociate into, let's say, H, OH, maybe H2 could also come, maybe O2 could also come, N could combine, we could get NO, and so on, we could get a number of species. Therefore, to be able to find out the products and their moles in the products, that means the concentration of the different species in the products, we define something known as Gibbs free energy, and for a given temperature, which would be the flame temperature at the given pressure, we said all these things will be in equilibrium, and that is what we were trying to do. For this, we also went ahead and defined something known as K equilibrium, which tells us the condition, that means the product of the pressures of each of the species are in equilibrium, and we defined this as K equilibrium, and using K equilibrium we were trying to find out what will be the products. And mind you, this dissociation or the number of species are important because the energy liberated in a reaction depends on the total heat of formation of the products minus the total heat of formation of the reactants with a negative sign. And if I have dissociated species, I may not get that much of energy, and my flame temperature or the adiabatic flame temperature may be smaller. Therefore, this is important, and that is why we were trying to calculate, and we illustrated this with the result for H2 going to H plus H, and we used the Gibbs free energy what was given. We could calculate the value of K equilibrium at two temperatures of, we calculated at, let's say, 300 Kelvin, and we calculated at 4000 Kelvin, and we found out maybe at higher temperature we get more of H because the K equilibrium value was higher, and we were able to write out, let's say, K equilibrium is equal to pH square, that is the partial pressure of hydrogen squared, to pH2, partial pressure of hydrogen, and based on the value we could calculate the proportion of this and the partial pressure. This is all we have been doing so far. But why did we say these things are important? This is important because in any chamber, let's say I have a rocket chamber like this, and at the exit of the chamber I have the nozzle which is expanding the products of combustion. This is at a pressure, let's say PC, which is quite high, let's say maybe 220 MPa or maybe 200 bar, 300 bar or so. I can always calculate the flame temperature, which we called as the combustion temperature. To be able to calculate the combustion temperature, I need to know precisely what is the products of combustion. We decided earlier, we said, well, if it is stoichiometric, I will have completed combustion products and I can calculate the value of Q. Once I know the value of Q, I know the specific heat distribution, and therefore I can calculate the temperature. I can also calculate the phase changes, the temperature change from the initial value to the boiling point at that phase change, and again boiling temperature to flame temperature for each of the cases. Therefore, we know how to calculate this for stoichiometry. When we said fuel rich, we made an assumption saying that if it is fuel rich, first the nitrogen in the fuel gets converted to N2 in the products, and it does not really give any heat. Then the hydrogen gets attacked by the oxygen and we get H2O, and then the balance goes to react with carbon, and this is how we did, and it was an approximate way of finding out what is the value of CO2, what is the value of CO. But then if I can do the same problem by assuming, let's say, that the products of combustion are at a pressure P, and if I now assume that the product of combustion is at a temperature Tf at a pressure Pc, and then I go ahead for each of the species or a combination of species, I put some chemical reactions, find out the value of K equilibrium, which we said is equal to minus delta into Gibbs free energy for the reaction divided by R naught universal gas constant into the particular temperature. Gibbs free energy at this temperature, at the assumed temperature, T at the flame temperature, I can calculate K equilibrium, and using this K equilibrium I can now calculate my products. And now I calculate the products, but I know that I have assumed this temperature, therefore I have to check whether this temperature is true, therefore I do the enthalpy balance. What is the enthalpy balance? My heat of formation of the products must minus the heat of formation of the reactants with a negative sign must be the energetics of the propellant, which divided by the Cp must give me back this temperature. If it does not give me, well, my assumed value is wrong and I must do it. Let me illustrate this through an example with which we had got started in the last class. Let's do this particular one. In this particular reaction or the reactants, what I take is hydrogen with A1 moles of oxygen, right. Now the reaction between hydrogen and A1 moles of oxygen gives me B1 moles of steam in the gas phase, B2 as hydroxyl radical, B3 as H atom, and B4 as O atom. I just assume it is true. We could have assumed something else. This is just to illustrate how we calculate the products of a reaction, and using the products of a reaction how I go ahead and calculate the flame temperature. This is what I want to illustrate. Therefore, what is it I first have to do? I must calculate the value of B1, B2, B3 and B4. If I know this, I can calculate the heat of formation of the products which are formed. I know the heat of reactants of this, and I subtract this and this with a negative sign, that will be my heat of combustion. If I know the specific heat of each of these constituents multiplied by the moles, which if I use the molar specific heat, I can get the temperature. This is what I want to do. Therefore, to do this, I first need to know what must be my value of A1. How do I get A1? Mixture ratio is specified. Mixture ratio is mass of oxidizer to mass of fuel, and we saw in the last class that the mixture ratio for a reaction such as involving H2 plus A1O2, the mass of oxygen is 32 into A1 divided by 2, which is 16A1. 16A1 is mixture ratio, and if the mixture ratio is specified, let us say mixture ratio of, we said, must generally be fuel rich. Let us say stoichiometric mixture ratio for hydrogen oxygen is 8, let us say 5, therefore this is equal to, I get 16 A1 is the value, I can get the value of A1. Whatever be the mixture ratio, I can do this problem. Now to be able to get B1, B2, I must be able to get the atoms on the left hand side to be equal to the atoms on the right hand side, and therefore I say I have 2 atoms of hydrogen, which on the right hand side I get 2 B1 plus 1 atom here B2 plus 1 atom here B3. This is the atom balance equation for H. Similarly for O, I have 2 A1 on the reactant side, and I have 1 O B1 plus 1 O B2 plus 1 O B4. Therefore, now I get 2 equations which connects the moles of my products, which I have assumed to be B1, B2, B3, B4, and which I want to determine for a given value of A1, and therefore I get these 2 equations. But then I find, yes, A1 is known, we just say for a mixture ratio of 5, A1 is 5 by 16, and therefore now I need to know what is going to be my value of B1, B2, B3, B4. I have 4 unknowns but only 2 equations, and therefore I need 2 more equations, and to get the next 2 equations I use the value of the equilibrium constants. And how do I use it? Well, let us say I assume, well, H2O could have dissociated to OH and H. If this is the case, then the value of equilibrium constant for this reaction is equal to partial pressure of OH into partial pressure of H divided by partial pressure of H2O. We said we could express either as a concentration, which is Kc, in terms of fugacity, but for ease we said let us use partial pressure itself. Or rather, from this equation I get pH, which is from the right hand side, I take it over here, is equal to Kp1 into pH2O divided by POH. I know now the value of pH in terms of pH2O and POH. Similarly, I would also like to get the partial pressure of oxygen, and for that I write the following three equations. H2 could have got dissociated to 2H, O2 could have got dissociated to 2O. For this particular reaction H2 to 2H, I get Kp2 is equal to pH squared divided by, that means I have pH into pH, pH squared divided by pH2. O2 going to 2O, I can write the reaction rate constant. For this I call as equilibrium constant, I call as Kp3, and Kp3 is equal to PO squared divided by PO2 over here. I have one more equation. I said, well, I can also consider H2 plus half O2 is equal to H2OG, that is gas phase, and therefore for this reaction I say the equilibrium constant is Kp4, and Kp4 is equal to partial pressure of H2O over here divided by pH2, and half O2 means PO2 half. Therefore I look at these three equations, and from this equation I get the value of maybe pH2 is equal to Kp2 by pH square. I get the value of O2 is equal to Kp3 by PO square. I substitute it in this particular equation and I get PO is equal to, I get the value of pH2O into Kp2, Kp3 half divided by Kp4 into pH square. How did this come? Let's take a look. I have pH square here, pH2 is equal to Kp2 by pH square. Similarly, I had in this case PO2 from this reaction, PO2 half is equal to Kp3 to the power half divided by PO. I substitute it and I get PO. I bring PO to the left side, I get partial pressure of oxygen is equal to partial pressure of steam into Kp2, Kp3 to the power half divided by Kp4 divided by pH square. Now what is it I have done? See, let's again take stock of why we are doing all this. What is it we said? In the products we have H2O, OH, H and O. That means we have 4 species, and now out of these 4 species what is it we have done? We have expressed PO in terms of pH square and pH2O, that is pH and pH2O, and also pH in terms of H2O and H. In other words, I take 2 of the partial pressures of 2 species, express it in terms of partial pressure of 2 other species. Essentially therefore we got 4 species. What were the 4 species? B1 of H2O, let's put it again, B1 of H2O, B2 of OH, B3 of H and B4 of O. Now we are able to relate 2 of them to the remaining 2 of them, and therefore now I can close my equation because I have 2 more equations, and therefore let's put it together again. Therefore, but before I put partial pressure, my equations are in terms of B1, B2, B3, B4, and what I have determined is partial pressure of H2OG, partial pressure of OH, partial pressure of H and partial pressure of O. Now how do I convert partial pressure to B1? I think that's something which is important. Let's just do it on the board. Let me again repeat what I am telling there. I have H2O, I have OH, I have H, I have O, and according to the equation what I have B1 moles of this, I have B2 moles of OH, I have B3 moles of H and I have B4 moles of O, right? Now what is it I did through equilibrium constant? I say the partial pressure of H2O is so much, the partial pressure of OH is so much, the partial pressure of H is so much, the partial pressure of O atom is like this. Now I have the atom balance equation in terms of B1, B2, B3, B4, but I have equilibrium relations which gave me in terms of partial pressure. How do I convert P in terms of B1? To be able to do that, if I can find out, if we can determine the total number of moles in the products, total number of moles in the products, then I can always go back and determine this. How do I say? Let us say that the total number of moles in the product are, let us say, NT, total number, and now the total number of moles of H2O is B1. Therefore B1 by total number of moles is equal to, I can now write this is equal to partial pressure of hydrogen divided by the total pressure in the chamber, and therefore I get B1 as equal to P partial pressure of water divided by, or steam, divided by the total pressure multiplied by the total number of moles. Therefore, if I can determine the total number of moles, it will be possible for me to convert the partial pressure of each of the species into their respective number of moles. Is it all right? Now, to do that, I cannot know, all I know is the total number of moles in the products according to this relation is B1, let me put it at the side over here, B1 plus B2 plus B3 plus B4 over here, but I still do not know the value of B1, therefore the total number of moles are not known. Therefore, we make an assumption, and the assumptions made is, let us assume that the reaction is stoichiometric, and based on this, if we keep working with this, we find that the total number of products which we form is not very different from the stoichiometric. Let's take that same reaction again. We said H2 plus A1 O2. If it is stoichiometric combustion, complete products of combustion would have been formed. Therefore, I would have got H2O plus, now what is it? I had 2 of A1, O had 2 of A1, I have consumed 1, I am left with 2 A1 minus 1. Therefore, the amount of oxygen left in this reaction as per this relation should be plus, I have 2 A1 minus 1 of O, but I would like to put it in terms of O2 which is left, therefore I get half over here. If I were to assume that this reaction is stoichiometric, I get 1 mole of H2O and I get the balance, that is 2A1 minus 1, which is depleted here, divided by 2 is what is left. I have therefore 2A1 minus 1 divided by 2 of oxygen which is left. Therefore, the total number of products which are formed, or total number of moles of products according to this reaction, if stoichiometric, is going to be 1 plus, I get 2A1 minus 1 divided by 2, which is equal to, I get now A1 plus half total number in the products. Mind you, this assumes stoichiometric, but the general thinking is, or general, if you do a number of problems, the number of moles are not very much different, but then we will go back and correct it as we go along, as I will show you. Therefore, to begin with, we will assume that the total number of moles what we are going to get is going to be A1 plus half. Mind you, it is stoichiometry. I am assuming, let the total number of moles in the products be this. If this is so, I now know the total number of moles over here, and therefore I can calculate PH2O as equal to B1 into P divided by NT, and therefore I do that next, and what is it I get? B1 is equal to, let's go back here, B1 is equal to PH2O divided by the pressure into the total number of moles, or therefore I can get the value of B1. Similarly, I get the value of B2 over here as a partial pressure of oxygen into the total number divided by the total pressure, B3 in terms of pH into the total number of moles divided by the total pressure, and B4 partial pressure of oxygen atom into total number of moles divided by the pressure. And what is it we have done? We have converted partial pressure of H2OG, partial pressure of OH, partial pressure of H, partial pressure of O into B1, B2, B3 and B4. But we already had the relation between B1, B2, B3, B4, and what was the relation we had from atom balance? We had 2B1 plus B2 plus B3 is equal to 2. We also had B1 plus B2 plus B4 was equal to 2A1 H2O. Therefore, we can use these two relations and we can now substitute for B1, B2, B3 in terms of the partial pressures, and we get 2PH2O plus POH plus pH divided by this particular one, that is we had to divide this to get P, this I bring it on this side and I get 2A1 into this one. I think this should have been 1 here and this should have been 2A1, therefore this is 1 here, and similarly I get from this relation PH2O plus POH plus PO is equal to the value of 2A1 divided by A1 plus half into the value of P over here. That means we have succeeded in putting the atom balance equations which were in moles in terms of the partial pressure of H2O, OH, H and PO. Mind you, we also had two other relations, namely we had the relation for pH in terms of PH2O, POH through the equilibrium constant, and we derived the relation for PO in terms of PH2O and pH square. Therefore, we have 4 equations in 4 unknowns, and what are the 4 unknowns? Partial pressure of H2OG, partial pressure of OH, partial pressure of H and partial pressure. We can solve this equation and determine the value of pH, PO, POH and PH2O. Mind you, the equations are not that linear or not, but we can always use some scheme like the Newton-Raphson scheme or some scheme to be able to solve this, and it can be solved very easily. Once we determine the value of pH, I must go back and determine the value of B1, B2, B3, B4. What I do? I go back, substitute it again in the equations for B1, B2, B3, B4, which we have here B1, similarly B2, B3, and now I get the values of B1, B2, B3, B4. That means I know the number of moles of H2OG, I know the number of moles of OH, I know the number of moles of H, I know the number of moles B4 of O over here. Now that means I know all this, but now I have assumed, what was my assumption? And the total number of moles was equal to A2 plus half A1, or rather this should have been what we had was A2 was 1, we had 1 plus half into A1, and therefore this was known to me, but I assumed this, but actual number of moles in the products is B1 plus B2 plus B3 plus B4. If this is going to be different from this, well, I assume this to be the total number of moles, redo the calculations till B1, B2, B3, B4 converges, and that will be my final value of B1, that is number of moles of H2O, number of moles of OH, number of moles of H and number of moles of O. In other words, what is it we are going to do? What is it we have done, or what is it we need to understand in this? We need to know B1 H2O, we need to know B2 how much of OH, we need to know how much of maybe H and how many moles of O are there. To be able to do that, we assume the total number of moles to be stoichiometric, and then we determine B1, B2, B3, B4. Then we said summation of Bi as I goes from 1 to 4 must be the same as total number of moles which we have assumed. If it is not so, now let me again assume N2 is equal to summation I is equal to 1 to 4 and take it as the thing, and again repeat the calculations till I get consistent or converged values, the same values of B1, B2, B3, B4 coming. We go through this loop, get B1, B2, and after I am able to get all these things to be the same, I go and write out my enthalpy equation again. And what is my enthalpy equation? I need to check whether the heat of formation of the products, I have B1 moles of water, heat of formation of H2O is known, B2 moles, heat of formation of OH is given, B3 moles, heat of formation of H is given, B4 moles, heat of formation of this is given, minus heat of formation of the reactants, hydrogen, and A1 moles of heat of formation of oxygen. Therefore, this is my net heat of reaction at the standard condition, and this heat partially goes into supplying the heat required to change the liquid hydrogen to its boiling point, then the phase change plus the change from the boiling point to the standard condition of 298. Similarly for oxygen, from the liquid state to the boiling state to the latent heat, and then the sensible heat or heat of the gas from the boiling temperature to 298, plus for each of the moles I have something like the specific heat into the number of moles into Tf minus 298 is what is given, and this must be satisfied if my values of B1, B2, B3 are correct at the temperature which I have assumed. If my assumed temperature is not correct, then this will not be equal to 0. I again have to assume a new value of temperature, calculate the value of Kp1, Kp2, Kp3, Kp4 at the new temperature, again do the enthalpy balance till my final temperature converges, and for this convergence I say that is my flame temperature. Let me repeat this procedure on the board a little bit with respect to the two convergences what we are looking for. All what we are telling is, well, I have something like K equilibrium for a number of maybe 4 steps we had K equilibrium 1 for a reaction. K equilibrium we said is equal to minus Gibbs free energy divided by R naught into T. To be able to get the equilibrium reaction, I need the value of temperature, because K equilibrium is a function of temperature. I first assume let the temperature of the reaction be, let us say 2000 Kelvin. Therefore, I evaluate delta G at 2000 for the particular reaction, just the same way as we did for the reaction in the last class. H2 is equal to H plus H. We evaluated it at 300, we have evaluated it at 4000. Similarly, I get the value of delta G at the assumed value of 2000. I have R naught 8.314 into 2000, I get the K equilibrium for a reaction. Similarly, I get K equilibrium for reaction 2 which I took. I find the K equilibrium 3, I take K equilibrium 4, which means I have assumed a temperature Tf. Let us put these two iterations together. To begin with, I assume the value of Tf, then I determine the values of K equilibrium. Then once I have determined K equilibrium, I again assume the value of total number of products which are available based on stoichiometry. Then I calculate the value of B1, B2, B3 and B4. Then I check whether the assumed value of Nt is correct, therefore this must first converge, and then I get the correct values of B1, B2, B3 and B4, provided that at this particular temperature. But then I use these B1, B2 in the enthalpy balance. What is it I do in the enthalpy balance? In the enthalpy balance, I sum up the heat of formation of the total products. That means I multiply by Bi into delta HFI for the products, minus I take the net heat of formation of the reactants, and where does this part of this heat go? It goes into taking, we had the reaction H2 plus half O2, it gave me B1 of the B1, B2, B3, B4. Therefore, I take the initial state may not be the standard condition. Part of this heat goes into the enthalpy required to convert the condition of, let us say, hydrogen from its original condition to the standard condition. That means I say I have the liquid phase, I have the latent heat phase, I have the vapor phase. Therefore, I have the heat required for H2, that is one of the fuel. Similarly, I have for the oxygen what is the enthalpy what is required, and again what happens is the balance of heat goes into sensible heat for the products and also latent heat as applicable for H2O, which I do not explicitly write. And this must be 0, right? This goes into this and to raise the temperature. Therefore, I get the new value of temperature. Now, from this equation, that is enthalpy balance, I say I have assumed Tf to be 2000. This might give me 2500, and therefore now I assume another value of Tf which is in between the two. I repeat the process till two successive values give me Tf around the same number. If I am interested in a very tight one, maybe I say yes, it must be 2501 or 2500. If I am not interested in such a close one, maybe I can put a wider tolerance, which means I do the problem. That means first my convergence is with respect to moles at an assumed value of Tf, and then I calculate for the value of Tf, and this is how we do. I like this method of equilibrium constants because you can see physically what is happening when you are doing it. I will also discuss something about another method which is equally powerful and which is used in many of the codes. We will discuss it. Therefore, let me again repeat this. You have B1, B2, B3, B4 determined, check the atom balance equations, again check for the total number of moles, repeat till this is satisfied. But then for this one we had assumed a particular temperature and calculated this, but the temperature was not known. Then to be able to make sure that this temperature is reasonable or some revision is required, I do the enthalpy balance for the reaction and then find out the final temperature and redo it till Tf is known. At this Tf I can therefore calculate the B1, B2, B3 and B4, which are the correct values of the dissociated species. Each of us will do for one specific thing using a computer programming, and it will help us in a lot of ways. We will do something like a project on this. But then see, it is also possible that some of the species what we talked of, let us say I have product containing CO2. Let us take an example. We considered monomethyl hydrazine. I will talk about it in the next class. You have hydrazine N2H4, you take one of the H and substitute it by methyl radical. This is known as monomethyl hydrazine. It is a very powerful fuel and it is used in many of the rockets. It is a liquid fuel, and if this is going to react with another oxidizer, we will consider it in the next class again, N2O4, maybe my products of combustion could be CO2. If my temperature is very high, maybe I could get CO. Maybe if the temperature is still high, maybe I could also get C of the G. But if my temperature is not so high, I could also get some solid form of carbon. Therefore, how do I distinguish between a gas phase and a solid phase? That also can be done using equilibrium analysis, K equilibrium, and this is what I show with respect to water and let us say liquid phase of H2O, which is water, and the gaseous phase, which is steam. I take the reaction H2 plus half O2 is equal to H2O. Therefore, I get the total number of moles of water should be the total number of moles in the gas phase but total number of moles in the liquid phase. For this reaction I can write Kp is equal to PH2OG divided by over here divided by, if it were all gaseous, I could have gaseous divided by PH2 by PO2. It need not always be fully gaseous. But how do I find out the percentage of water? If I can calculate the temperature, and in the once I know the temperature, I can always calculate how much of steam will be there, because steam is saturated at that particular temperature. I can get the partial pressure of gas from vapor pressure table, and if I know the amount of what is available, I calculate the hydrogen and oxygen, I know the total pressure, and then once I know the proportion of gas from the vapor pressure table, I can go back and determine what is the balance of this, and this is how we calculate the proportion of phases. And this happens especially when we have solid propellant rockets. I will consider solid propellants in the next class again. We add lot of aluminium. Aluminium forms Al2O3, and this Al2O3 could be as a liquid phase, could be as a solid phase when it is coming out, and all these things have some energy in them. Therefore, we must be able to calculate out, and those of you who do a project using solid propellants must be able to differentiate it. But the procedure is extremely simple. Okay, this is all about calculation of the species, but there is also another method which is normally followed in many of the codes. Whenever we deal with rocketry, they say the first thing what we do is, yes, I use NASA SP273, which gives me a computer program. This is widely available, it is available here also, but this has been refined, and now we say there is something known as Cosmic which is available. It is just the SP273 in a more user friendly version. What they do is, instead of going ahead and finding out the equilibrium constants and then finding the temperature, what they say is, let us say Gibbs free energy we define at constant pressure and temperature as equal to Nj mu j, and therefore I can say the total Gibbs free energy is equal to the, let us say in our particular case, let us write out the value of the Gibbs free energy what we are going to get. for the products which we need to determine, we have B1 of H2O, we had B2 of OH, we had B3 of H, we had B4 of O. Therefore, the total Gibbs free energy is equal to mu of H2O into B1 plus mu of OH into B2 plus mu of H into B3 plus mu of O into B4, right. This is the total Gibbs free energy. And what we said, when Gibbs free energy is a minimum, that is the equilibrium. Therefore, if I put G as a minimum, or rather if I were to put dG as equal to 0, I should be able to find out the value of B1, B2, B3, B4. And this is a very direct procedure, but it is little involved. Let us see what is involved in it. But this set of dG equal to 0 must also obey the constraint that the atoms must be conserved. And what did we say? Here we had H2 plus half O2, and what were our atom balance equations? 2 is equal to, or let us put the right hand side first, 2B1 plus B2 plus B3 minus 2, minus 2 equal to 0, and for O balance I had B1 plus B2 plus B4 minus, if we had into half of, we had A1, isn't it, H2 plus A1 oxygen. This was our reaction. It was not half O2, it was not stoichiometric anyway. Therefore, I have minus 2A1 equal to 0, and this 2A1 we determined based on mixture ratio, right. Therefore, these were the two equations which have to be satisfied, because I cannot create atoms in a reaction, and therefore we call this as the constraint equation. Even though I have to minimize the value of Gibbs free energy dG equal to 0, this must also be obeyed, and therefore we use the method of Lagrangian multipliers, which is what I show here. I define a Lagrangian L, which I say is equal to L is equal to G plus, this is the summation. I have two species, L is equal to 2, I is equal to 1 to 2. I wrote this out, B1 minus B prime, Bi dot is the left hand side, where Bi is equal to the stoichiometric coefficient into this was equal to B1 into H2O plus B2 into OH and so on, and therefore this plus this, in other words, let us put it back again, I should have Lagrangian I define as equal to G plus lambda into, I have this equation coming over here, must be, this is what I define as a Lagrangian, and then I go ahead and tell myself, well, Lagrangian could be 1 and 2, because I have two such equations. Therefore, lambda I have two of them, and therefore I say dl by d lambda must be 0, and this is the method of what we call as optimization program, or optimization or linear optimization. G is equal to this plus this, therefore del L is equal to, I differentiate over here, and I get with respect to Nj, I get mu j plus summation over lambda I Aij dnj plus the product minus the initial reactant into d lambda I. The differentiation of the moles of the products cannot be 0, the Lagrangian multiplier is a free multiplier, it cannot be 0, and therefore we get this is equal to 0, we get this is equal to 0, we get a set of 4 equations which we solve, and that gives me the value of B1, B2, B3, B4. Maybe you all should learn to do both of them. I have never really used the Lagrangian multiplier method, but when I went through the SP273 book, I found it's quite simple. I personally like the method of equilibrium constant, because I am able to see everything come through. In this again we have the 4 matrices which we have this matrix involving B1, B2, B3, B4 which we solve. I think this is how we solve this, and we determine the products of combustion, and once the products of combustion, you know the heat of reaction, you know the Cf, once you know the distribution of B, I can find out the value of Cp for the mixture, I can find out CV for the mixture of the products, I can find out the gamma, and I can determine whatever be the performance I want to determine. And let's take a look at the results again. I did present this earlier. Now let's see, having understood the problem or having gone through it, let's say how the flame temperature changes with mixture ratio for a hydrogen oxygen reaction. Mixture ratio 8 is stoichiometric, and as I said, we always operate in the fuel rich region. Now at higher pressure I find a higher value of temperature than at lower pressure. Why is it? At higher pressure, the gases cannot dissociate because you are forcing the gases into a smaller region, and therefore you get more completed products of combustion at higher pressure, and therefore the temperature is higher. As pressure reduces, I come to something like 10 bar, that is 1 MPa, the temperatures are much lower than at 1000 MPa. Therefore I find higher pressure the dissociation is less, and I can get a higher value of flame temperature. See, we are able to interpret now, having understood the problem. Let's take a look at the molecular mass of the products. You find over here the molecular mass of the products increases as the pressure again increases. At 1 MPa it is evolving a little bit lower. At a higher value of pressure, maybe I get a higher molecular mass. Why is it? Because I get more completed products of combustion which cannot dissociate. Because of higher pressure, I cannot have too many moles, it is shrinking, and therefore my molecular weight also increases as the pressure increases. But I do find, if I go back to my previous one, I find that the change in temperature is quite enormous, whereas the change in molecular mass is little bit. Therefore the ratio of, let us say, under root Tc by the molecular mass will still be large, will still be higher at higher pressure, and therefore a higher pressure gives me a higher value of performance. Let's take a look at some more things. Let's take a look at gamma. Gamma, we said for the simple species like a monoatomic species it was 1.67. For more complex things like CCl4 and all that, it was lower at 1.12 or something. And what is it we find? We find that at higher pressure you have more complex products, and therefore the gamma is smaller. As pressure reduces, the value of gamma decreases, which is again in the right direction. Now I put the value of gamma, everything together, and calculate my ISP value. I find, well, at higher values of pressure like what is shown 100 MPa, I get a higher value of specific impulse compared at a lower pressure. But something more important, the peak values is somewhere over here at 100 MPa. As the pressure decreases, I get more and more fuel rich gives me a higher value. That means the choice of the mixture ratio which gives me maximum performance also depends on pressure because of the dissociation. I think these are the important conclusions which we draw from these particular slides. I think this is all I have about the slides, and now let's go back and try to understand the last part of why we do all this equilibrium analysis. As we say, are there certain things which we need to understand further? One thing I want to qualify is, when I put the ISP in that particular plot, it is ISP at sea level, because we found ISP will change, right? At sea level the ambient pressure is 1 atmosphere. Okay, now let's consider the last part of the dissociation before we can look at the chemical propellants for their characteristics. What we have been talking of, we have a combustion chamber wherein the pressure is Pc, the temperature is Tc. We now know how to calculate Tc, which we said is adiabatic flame temperature. We also know at this adiabatic temperature what is going to be the proportion of the products B1, B2, B3, B4 and so on. All these products from the combustion chamber, I deliberately use this because let's not think that a rocket should always be a cylinder and all that. This is a combustion chamber. This feeds into my nozzle. Well, nozzle is like this over here. This is the converging part of the nozzle, this is the throat, this is the convergent, and this part is the divergent part of the nozzle. what is it we have done so far? We have determined the products of combustion, that is moles of the products, the flame temperature as the gases enter the particular nozzle. Now what is going to happen? What is going to happen to the flow over here? In our previous work on nozzles, we assumed, yes, I know B1, B2, B3, B4 here. I can calculate the value of gamma, I can calculate the value of M, I can calculate the value of Tc, and using the relation I got ISP for a one dimensional flow based on these products. In other words, I assume that the composition remains the same everywhere, the value of gamma remains the same everywhere, the value of molecular mass remains the same everywhere. That means my flow is taking place, flow through the nozzle is taking place as if the composition were frozen. And what did I determine, and what did we determine? Let's plot it. We determined the variation of, let's say, temperature from the adiabatic flame temperature which we have just calculated, and as it goes on, it goes this, we have the throat at Mach is equal to 1, right. But now there is some subtle difference. Now as the flow takes place, temperature drops, therefore let us take a section here. Now let me take a section over here, let us call it a section 1, let me take a section 2 over here, just to illustrate the phenomenon. That means I take this is my section 1 of the nozzle, that means I take it in the convergent, I again go ahead take a section in the divergent, this is 2. At section 1 the temperature is, let us say, T1, at section 2 the temperature is T2 over here. Now what is it I find? I find T1 at section 1 the temperature is less than the flame temperature. Let us put it down because this we need to be absolutely clear about it. That means in the convergent when I had a section 1 the temperature was T1 which is less than the flame temperature Tf. If the products are going to be equilibrium at this section 1, well the proportion will not be B1, B2, B3 and B4 as we calculated at Tf, but since it is cooler perhaps the composition will be different, it will be B1 corresponding to the new value of T1, similarly B2 corresponding to the new temperature T2 and T1 and so on. In other words, in practice as the temperature gets lowered I will get a new composition here, and when it has expanded quite a bit maybe the composition will be totally different. In other words, the composition of the products B1, B2, B3, B4 whatever be it for a given reaction will keep on changing as the flow takes place. Therefore I say in practice composition of the gases or the molar composition which we are considering will keep changing. As the gas expands I am going to get a new equilibrium constant and that is going to give me a new type of B over there, and how do I solve this? In other words, the composition keeps shifting, and such type of flow in which at each point the composition shifts is known as shifting flow, shifting equilibrium flow. Because the equilibrium shifts I call it a shifting equilibrium, and this is a equilibrium flow. Well, to solve this is extremely simple. I go to the next section, I find out what will be the temperature for this particular expansion assuming the values of gamma corresponding to the earlier section I can find out. At this point I find out the value of the new species, I can calculate what is I revise temperature again, revise products again, and so on I can do using a chemical or let us say a shifting equilibrium. And what happens in shifting equilibrium, because the temperature drops I get more of the products which are not dissociated, because at low temperatures I cannot get dissociated, heat gets released, and therefore if I were to plot my value of heat release which I took Q of the combustion along the nozzle, I did not consider heat release at all. In practice because of this heat gets released and Q gets released, and therefore whenever I calculated the temperature distribution in the nozzle like this based on expansion, actual temperature will increase, and therefore because the temperature has increased my ISP, my value of specific impulse, corresponding to shifting equilibrium will be greater than ISP corresponding to equilibrium. Is this point clear? This is important. But now how do I determine which is how should I use? In my convergent the flow is quite subsonic and therefore I have lot of time for reactions to occur. In my divergent where the flow is supersonic, there may not be time for equilibrium to take place, and the general practice what we find is, well, you assume equilibrium flow or shifting equilibrium flow up to the nozzle throat and frozen thereafter, and this seems to give the value of specific impulse to be near the values what are experimentally measured. But this is not always true. It depends on the type of gas, the type of dissociation, but for hydrogen oxygen there has been published work, they have Bray model and all that, which assumes, let us just put it down, supposing I have a nozzle, convergent followed by divergent, I have in the convergent shifting equilibrium flow and in the divergent frozen, which tends to give me a reasonable value. If not, what is going to happen to me? I have specific impulse which I consider, let us just make a last plot of it, and then we will say versus mixture ratio. If I were to plot specific impulse, this is my stoichiometry, this is fuel rich region, in the fuel rich region I will get the maximum, this is for frozen flow, for equilibrium flow maybe I will get a higher value, and the actual will be in between the two, and this somewhat matches with equilibrium flow in the convergent followed by frozen in the divergent. I think this is all about dissociation of gases, the characteristics of propellants we have seen, and maybe in the next class we will take a look at the different types of propellants. Okay, thank you then.